Hello, my name is Arezi Aki, and this is my Lab 2 on falling motion. The purpose of Lab 2 was to observe the effects of drag and gravity on an object in falling motion. Using Tracker and VPython, we were to observe the variances of the object's motion in two events. I observed it in three. One, the effects of only gravity. The second, the effects of gravity and drag. This wasn't required, but it did help my understanding of the lab. And the third was the effects of gravity and turbulent drag. Here's a video of the motion I observed. My predictions were as follows. The effect of drag, which is a force in the opposite direction, on the object should cause the object to slow a bit as it falls to the ground. It should increase as the speed of the object increases. Since the object I observed was in a non-manipulated environment, the curve result in Tracker should more closely emulate the curve generated by the formula, which accounts for gravity and drag. However, the object's trajectory will most closely emulate the model accounting for gravity and turbulent drag. So working in Tracker proved to be a bit easier this second time around. The points selected show that the trajectory of the koozie is half of a downward-facing parabola. My initial conditions observed were that y initial is 0 meters, velocity initial is 0 meters per second, and delta t is 0.77 seconds. The effect of gravity is, well, how I calculated it, first of all, was to calculate the weight of the object. So the mass of the koozie was 0.0085 kilograms, and the weight of the object is the mass times the gravitational constant. So the weight of the object came out to be 0.0864 newtons. Initially, the gravity-only model proves to be a good predictor of the koozie's motion. However, as you can see, as the model progresses, the gravity model predicts the koozie's path past what was observed, and that's what all this disparity is right here. This was not required, but this is the effect of drag and how the models compared. The formula for drag is the proportionality constant times the velocity of the object. And as I predicted, the curve of the model accounting for both gravity and drag is a better prediction of the motion of the koozie. In this, I had to change the b-value. I changed the b-value to 0.025 so that the last observed position value and the last calculated position value were close. And as you can see, the disparity is quite less because of that. So keeping with that model, I went in to study the effect of turbulent drag on the koozie. This was stated in the lab problem description, and the formula for turbulent drag is the proportionality constant negative times the magnitude of the velocity squared. As I predicted, the formula for turbulent drag does prove to be the best approximation of the koozie's motion. In order to get the values to be similar to the last observed value, I changed the b value to negative 0.0115. Last but not least was calculating the aeroscale. Using what was shown in the video, I took the weight of my koozie, which, if you remember, was 0.0864 newtons, and I chose the length of the arrows to be 2 meters. So using the formula in which the length of the arrows is equal to the weight times the aeroscale, I calculated the aeroscale to be approximately 20 newtons per meter. The magnitude of the drag force of this object is quite large, and it's larger than that of the paper ball in the example, no doubt due to the holes in the surface of the koozie, one for the actual can to enter and two on the sides, I guess for decorative purposes. Thus the arrow for the drag force is large. So in order to visualize the effect of drag on the object better, I changed the arrow scale down to 10, and as you can see in figure 1.2, it just provided a better visualization of the effect of drag on the object. So that is what I did for Lab 2.